Welcome back, geologists, for the second half of the Paleogene and Neogene plate tectonics. So you just learned about some of the key elements on a worldwide basis. Now let's focus in on the geological provinces of North America. When you look at North America, we're going to kind of take a zoomed in look at this, and we're going to show you different parts of the provinces of North America. So in your book, it reads this way, and most textbooks do, because it's so amazing how much history we have in Cenozoic that it's kind of hard to tell a nice flowing story. So I've tried to smooth that story out for you to make it a little bit more reasonable. So we'll be talking about, for example, the Columbia Plateau, the Basin and Range, the Colorado Plateau. We'll talk about the continental interior. Then we'll come over and talk about the Appalachian and the Gulf Plains down here, the Gulf coastal area. So understand that I realize that this can be, it kind of jumps, I get that, but not nearly as much as your textbook reading does. So I tried to really intentionally do this for you because it's almost can make you dizzy how much stuff was happening all at the same time. So let's start with the Cordilleran mobile belt. We know that back in the late Cretaceous that the Laramide orogeny began, right? And we know that we had the Nevadan, Sevier happening during the Cretaceous, and they were a big deal in terms of uplifting mountains, but their Nevadan and Sevier uplifted much more towards the typical about 150-ish kilometers or even just a couple of hundred miles inland. Now, when we think about the Laramide orogeny, a different ball game, and this is a nice scaled map to show you in terms of distance. If we're looking at the true Rocky Mountain frontal range right here, this is where the Rockies are, it's more than 500 miles inland. That is really strange. So the Laramide orogeny may have started in the late Cretaceous, but it's going to go through the Eocene epoch, and that's kind of important because the Eocene sets the stage for this another round of some serious volcanism that's going to occur in the next epoch. So what we're going to see forming the Rocky Mountain Range is a unique set of circumstances where we see minimal volcanism. Don't get me wrong, we had it. And some of the volcanism we had was extremely dangerous. But what we do have is massive block faulting, so these big sections of mountains got thrusted upward. That's why the Rockies look the way they do. They're big fault blocks that have been created horst and grabens, for better lack of words. And so we're going to take a look at how that formed. So we'll start with the Laramide orogeny, and we can't have a discussion about the Laramide without talking about how far inland it occurred. We just established it was more than 500 miles inland. Well, that's weird, very weird, because most subduction zones happen within several hundred kilometers of where the trench of the subducting ocean plate occurs. So usually they're on the far edge of the side of the margin of a continent that's being impacted. Having said that, we have this weird situation where we get the Rockies uplifted, and modern Rockies that is, uplifted in more of the interior section of the continent. Well, that's strange. What's up with that? There's a lot of controversy about how this occurred, and your book did a really good job of describing multiple sides of the story. And in science, remember, you always need to look at all plausible potential explanations and let data guide you to the right answer. In this case, the most accepted theory that's out there is the shallow angle, and I would say geologists don't argue about the shallow angle. That's a fact. We know that. We can see that by the rock record. So we're not going to debate the shallow angle. And remember, it's about 10 degrees. It's almost flat. It's going to come in and it's going to increase the friction with the continental crust above it. When this occurs, that crust kind of splits, and when it does, it creates fault zones, and these big, huge fault zones are going to push blocks of rock up, and others are going to fall, and crust is going to pile one on top of the other, and it creates a very big set of mountains called the modern-day Rocky Mountain Range. Now remember, the Laramide is very low angle, unlike the Sevier orogeny. So it is a unique orogenic belt, and one that's studied globally because of its unique character in terms of how did this plate slow down. We know that the Rocky Mountains were not just the only area in the United States. When you consider the Rockies, we can also talk about the northern extreme of the Rockies, which are found in Montana and Western Canada. When I went on sabbatical, I was fortunate enough to go to Glacier National Park, and it's really called Waterton Glacier International Peace Park. That's actually its real name. And so the Waterton is the Canadian side, the Glacier National Park is the US side of that park. This is a famous feature that is in the park, and it represents the Lewis Overthrust Fault. In some cases, this stuff moved over 50 kilometers, and your book talks about this. It's really quite remarkable about how this movement along where the laramide had happened, this crust was subducting, but at such a low angle, it caused this massive movement and buckling of the continental crust above it, and it shoved it, is what happened. And this is an evidence of this. It's a very famous place that you can see the Lewis Overthrust Fault, where it just pushed crust further away from where it used to be in terms of many tens of kilometers. When we're talking about the laramide orogeny, that is going to be long gone and over with before we talk about this next place. The Columbia Plateau was one of the places and regions I wanted to visit on my sabbatical, because I'd done all this research and I'd heard about it, I'd seen pictures, but I really wanted to understand it. And that's what geologists do, is go out and see stuff, right? So they can get a better understanding of what's going on. This material was deposited during the Miocene epoch, so it's Neogene in age. What's incredible about it is that it's a flood basalt, and when I mean flood, remember from physical, flood basalts represent runny lavas that can travel for, in some cases, 50 miles, certainly tens of miles away from their source, and in this case, even further. What's weird about this stuff is that it originated from volcanoes that came about during the Miocene epoch, and we have 7,500 feet thick of this material in this region. Now, it makes this incredibly gorgeous river basin, and the Columbia River goes right through it. So I took a boat ride to get a tour of the area, and this is where these shots came from that I'm showing you. So we're looking at the Columbia Plateau, and essentially the plateau is called that way because of this thick amount, the 7,500 foot thick material that has created a big block in which most of Oregon and parts of Idaho and even a little bit of Washington State sit in, but a bulk of it's in Oregon. And so it makes for a pretty awesome set of river basins, like the Snake River and the Columbia River go right through this area. If we're going to talk about what was going on during the Cenozoic and certainly during the Neogene, we have to talk about the Cascades. The Cascadia Range involves volcanism that formed as a consequence of, in some cases, the laramide, and current volcanism that's being caused by the Grande Fuca plate, which is a leftover of the laramide, specifically the Farallon plate. So you'll find volcanism in Northern California. You'll find it in all the way through Oregon and Washington State, which is where one of my legs of the sabbatical I went on traveled to. Oligocene epoch was when a lot of this happened, but it even continues today. So it dates back that far back, and you're looking at Mount Shasta right here. And Mount Shasta is actually in Northern California. And see these red dots right in here? This is the Cascadia Range, and those are volcanoes. And there's a stretch of volcanoes that exist all the way through this region that represent active volcanism. Well, there's another part of the continental United States that's worthy to talk about in Cenozoic, and that's the Basin and Range. So the Basin and Range, most of it is in Nevada, with a little bit being in Utah, some in Southern California, and a tad bit in Arizona. And if you really want to even be, some of it's in New Mexico. So what does Basin and Range mean? I'm going to show you a diagram in a minute, so hang tight. But essentially you get uplift and then you get a drop. Uplift and a drop. So crust has been pushed up, and well, really what's happened is it's been stretched, so it's been pulled, and so it appears that some crust is higher and some is lower, when in reality what's happened is the crust has dropped. And so you've got this up and down section, and as differential weathering sets in, it makes little mountains and then basins, mountains and basins, mountains and basins. Now they're not the same size as something like the Rockies, but they're definitely highlands. We also know the Sierra Nevada area was uplifted Pliocene again with some impact of tilting of those rocks, and that tilting did a really important attribute. It's going to tilt. If you've been to Yosemite in this area right in here, Yosemite, you have to travel over this big, big, giant mountain to get to the eastern interior continental side of the Yosemite. And that's the way we traveled in when I went on my sabbatical. And it was just gorgeous to see this change, because you came from a very arid environment and you cross into this completely alpine area. So here's what's happened. When this tilting occurred, essentially the Sierra Nevadas tilted high enough that they block out weather systems from rarely hopping over the mountain, and this is what's on the other side, Death Valley. So Death Valley is a rain shadow desert. Now you learned that in physical, you know about rain shadow, but this is an active rain shadow desert today. So when you go, if you get a chance and you get to go to this area, you need to visit both of these places in the same trip, if at all possible, so you get the real understanding of the difference in climate. And it really will hit home with you how significant rain shadow is. The next theory deals with just your plain old hot spot beneath a continental mass where a magma plume stretched the crust. This one actually seems pretty plausible to me. San Andreas fault movements have created crustal deformation. There's a lot of truth to that as well, but not necessarily as far inland as where most of the basin and range is. So that's why I kind of think that we've got a series of these things that have cooperatively worked, whether it was, it happened all at the same time or segmented over a period of time for the basin and range to form, which is true. We know that not all areas formed exactly at the same geologic time, just over a stretch of the Cenozoic. It's just real easy to understand because we've got this stretched out land where you've got a bunch of flatlands and highlands. It's not that simple. It's actually very complex geology, and it differs from region to region within the Basin Range province. One of the most fun parts about the Cenozoic is learning about the Colorado Plateau, where most of the rocks that are in the Colorado Plateau are Paleozoic and Mesozoic in age. There's certainly some Cenozoic rocks there. But the real newsworthy event is, when did the Colorado Plateau start to get uplifted? That starts the development of something like the Grand Canyon. During the Miocene epoch, right around 20 million years ago, the Colorado Plateau began to uplift. And understand this was a gradual process. So you'll hear different ages put to that: 15 million years, 10 million years. But really, it started somewhere around 20 million years ago. And when it uplifted, it really pushed the entire plateau upwards by about 4,000 to 6,000 feet in elevation from where it used to be. So it is a true plateau, and it makes up the Four Corners area right in here. This is the Colorado Plateau area. And when this process occurred and this land got uplifted, almost like you shoving an entire box up onto a high place in your closet, this area fractured and it faulted and it reactivated faults. And so that's how the Colorado Plateau started splitting apart. It put a lot of joints in areas, things like Bryce Canyon National Park, places like Grand Canyon National Park, Zion National Park. The Colorado Plateau is a poster child for what happens when rocks get fractured, and then on top of that, they get tilted. So if you tilt rocks and it tilted towards the north, what's going to end up happening, if you tilt even just slightly, water starts to run downhill. And that's what helps create these wonderful canyons that we see throughout the Colorado Plateau, like the Grande Canyon right here. Another worthy place to talk about, and very important to The southern section of the continent is the Rio Grande Rift. Now, this is a fairly long area of about 1,000 kilometers, and it's really interesting. It goes from Colorado all the way down to parts of Mexico, but certainly throughout the state of New Mexico, very much impacted by this. And what's happened is we have normal faults that are on either side of this, and you need to think about why. As a rift zone pulls apart, it's caused by tension. So that tension is going to create normal faults. And this rifting has had a series of episodic events. First and foremost, it started around 29 million years ago in the late Oligocene epoch. And when it did, it lasted for about 10 to 12 million years. And then we would see it conclude for a while in the middle Miocene. Just briefly though, because literally a second phase or flux happened of rifting shortly thereafter in the middle Miocene. That's a different event, and it began to split it apart again, and that started 17 million years ago. It's still occurring today. A number of evidences for that. It's moving at a very slow rate of about 2 millimeters, not centimeters, millimeters per year. What's some of the evidence? Lots and lots and lots of lava flows, and we'll get into some of those when we get into the Quaternary. We can't talk about plate tectonics in the Cenozoic without talking about the birth of the San Andreas Fault. So the San Andreas is infamous because it is one of the few faults that we can actually follow at the surface. Most faults are actually subsurface. You can't really see them. It's just an expression at the surface that the Earth is moving beneath it. During the Oligocene, we are going to see the Pacific Farallon Ridge collide with Southern California. So we had a subduction zone there for a while the San Andreas today has nothing to do with subduction. It was initially created by a triple junction of plate collisions that occurred in this area. So you need to know about what those plates are because they set up the dynamics for the remainder of the Cenozoic plate tectonics. And I might add, still happening today. We have an intersection of the North American plate with the Pacific plate, and then, of course, the Juan de Fuca. That's going to be up in the Pacific Northwest, where I was talking about Oregon, Washington State, Northern California. Now, if we're thinking about the one that's down by Central America and Mexico, that's the Cocos plate. So the same 3 plates minus Juan de Fuca substituted with Cocos. To be clear, both of these plates are leftovers from the Farallon. So as North America plate moved across westward, and that's how we're moving today in a northwesterly manner, over the Pacific plate, these caused these triple junctions to be relocated. And as they're relocated, this caused now the Pacific plate to simply drag against the North American plate. So now we have a transform plate boundary at the San Andreas and not a subduction zone. Well, the continental interior is not without a story either. Some really great things happened during the Cenozoic in the continental interior, and one of my favorite places in the middle of our continent is the Black Hills in South Dakota. We consider this area, when you're looking at the Great Plains, this whole section of areas, so even parts of Texas are considered the Great Plains. And really, even just a couple of hundred years ago, this was such prolific grasslands that you could walk out the back door of Waco, Texas, and be standing in 6-foot-tall blue stem grasses. So obviously something's changed, right? Now there's still some areas, when you think of the plains, that aren't used for agriculture that still have that same grasslands. And some areas are even protected by national grasslands and been set aside for conservation. By the early Paleocene, which would be the beginning of the Cenozoic, we know the Zuni Sea was regressed off the continent in Craton, except for one area, which is kind of interesting. It's going to be this state right here, North Dakota. And as the highlands that were uplifted during the Laramide orogeny, as they start to shed their sediments, they're going to fill this whole area in with stuff. And that stuff's going to be important. So if you're right around where North Dakota is, right here, you would probably have some marine environment rocks, but most everything's going to be transitional to true detrital material. One area that we can see some excellent evidence of this is in the Black Hills of South Dakota. It provided a local source of sediments that were being eroded to fill in the continental interior. Now, if you look at this picture very carefully, Black Hills, and specifically where this is, let me just kind of say it's right about where the B is in black. This is not too far from Flagstaff, so if you're going up that way to see Mount Rushmore, there's so much to see just besides Mount Rushmore, but that should be like one of your priority stops. And there's a highway called Needles Highway that's actually made out of Precambrian granite. Now, we talked about that back in the Precambrian lessons. What's important, though, is that that stuff is still shedding sediments, and so it's obviously pretty durable and tough, but it does provide for some important resources. And then rock layers that got stacked on top of that also provide us excellent resources that we can use for economic gain. One of the areas right by this section of land, and it's actually in South Dakota, is called the Badlands National Park. Now, Badlands is simply a term that we've already classified in this course for lands that really can't be used for agriculture. They're typical of what we saw with the Chenley and the Morrison Formation. This park is made up of sedimentary rock layers that contain sand, silt, and clay that were deposited starting in the late Cretaceous, but most of them are early Cenozoic in age, so from the late Eocene all the way through Oligocene epoch. And we know we have varieties of depositional environments from marine to tropical land, forest stuff, meandering rivers, and each of the rock layers tells a story, much like the Grand Canyon, just like any of these parks that we've learned about, right? So you're looking at it, you're like, well, that looks just like the Morrison, it looks just like the Chenley. Well, it's not. It's a different set of geologic formations. But the Badlands is very famous because it contains some of these early mammals that are preserved in these sedimentary rock layers. So if you get a chance to go out that way, I would make that stop. If you're coming from the Texas area or even from the East Coast area, you'll likely be driving right by it, so it's worth a stop to see it. Another area that is a must-do thing if you are going to this area is in the eastern side of Wyoming called Devil's Tower. This is depending on who you talk to, a volcanic neck or the remnants of a laccolith. I am more along the lines of saying it's volcanic neck. It sure looks that way to me. But nevertheless, there are competing theories, and I should share those with you. But one thing everybody agrees on, that it occurs during the Eocene epoch, and it's a volcanic system that is representative of the volcanism going on during the Eocene in Wyoming. So there's a number of theories. As a matter of fact, your book had a whole section about this and the stories that I have shared even in physical, if you took physical with me, about the bears trying to get to the top of this thing, and that's what the scratches represent. Well, we know it's really columnar jointing. I don't think the science story is as exciting as the Native American legends. But nevertheless, it is a really fascinating deal. So you might wonder, where's the rest of the rocks? I mean, wouldn't there have been a volcano there? The answer is yes, but they're gone because this has a very low differential weathering capacity, meaning it's pretty durable, and all the sedimentary rocks and lava flows that used to make up the big volcano that used to be here is gone. It's eroded away. So this represents volcanism in the Eocene in the continental interior. Devil's Tower is really a fascinating place to visit. Well, another place to talk about in the continental United States is the Appalachian Range. So there's a lot of controversy. Is the Appalachians really rising or not? Well, we know they're isostatically rising, and isostatic rebound is, we'll talk a lot more about that in our next lesson, but nevertheless, these mountains have been around since the late Paleozoic. Really, to be honest, most of them have been eroded to almost a flat plain by now. So how in the world do we get any uplift at all? Probably the most accepted consensus of the theories that are out there is this, that these got kind of by the fault action that was happening throughout the continental interior, these areas got impacted by that, which caused some sections that got dropped to start eroding by rivers, and these large rivers created water gaps, which are essentially places where rivers can flow, which rivers don't there today, and wind gaps that had no water at all. This was occurring during the Miocene, and now today the Appalachians are uplifting from isostatic rebound only. So really, there's really not a plate collision that caused any of this to occur. All right, we have to talk about the final slough sequence. Yay, we're done with sloughs after today. Except for your final, of course. But nevertheless, the Tejas Transgression is the very last of the 6 slough sequences, and it started at the beginning of the Paleogene and went through the Eocene epoch. Now, let's talk about this. The Tejas Sea, Paleogene to Eocene. Doesn't sound like a big, huge amount of time, but it's enough to do some really important stuff. This was a wimp compared to something like the Zuni or the Tippecanoe or the Kaskaskia or the Arab-Soroka. I mean, it's not even close, but what it does give us is huge volumes of oil and natural gas. So it is worthy to talk about. Now, you're going to find loads of this stuff down here around the East Coast, the Gulf Plain, or the Gulf Coast region, and then, of course, the coastal area of California. You'd expect to see rocks from the Tejas Transgression. Believe it or not, the Tejas actually invaded the Mississippi River Valley and went all the way up to southern Illinois, so you can find rocks that were marine up in that river basin. Beyond that, there's minimal Tejas Transgression rocks, so let's talk a little bit about the importance of these rock layers. This is really worthy test question stuff. There were 8 minor transgressive regressive cycles within the Tejas. This is so important because the sea level would slightly rise and fall 8 consecutive times. It would leave behind this remarkable set of rock record. Some would be excellent for holding groundwater, which certainly is the case for Texas. Some of it would be excellent for holding oil and gas, another Texas thing. But what we need to really think about is, how does Texas, Louisiana, even Mississippi and Alabama differ from Florida? Florida was fully covered by the Tejas, so it experienced carbonate deposition much like Texas did during the Cretaceous period. However, our areas would have been slightly flooded for brief periods of time off and on, and then as those microorganisms die off that contain that oil that we learned about earlier in the semester, they're going to make huge thick layers of this. And one area in particular I can think of is the PETM, where a huge amount of microscopic phytoplankton went extinct. And they are going to help set the stage for all these yellow dots, which happen to be active platforms that are oil rigs. So this is totally in tune also with connecting the dots and linking it back to Jurassic, where the Luan salt domes are, if you have a recollection of that. So we need to talk about the Luan salt domes. Remember, those are Jurassic in age, and they're up to 4,500 feet thick. So here's how this works. Salt is kind of a funny thing, especially when you get a huge accumulation of it. It will start to rise because it's very low density, and as it rises, it fractures the rocks below it. So it actually, here's your rock layer down here from the Jurassic, and it's going to run through all these younger rock layers like Cretaceous and Cenozoic. And when it does, it fractures and deforms the rock above it, creating fault zones. Those fault zones are important because as the salt dome squishes up, you're going to get oil and gas from these layers, for example, trapped in these things called structural traps. And this is an anticline feature right here, since from physical you'll remember that. And so we look for these salt domes because they're characteristic of also allowing the oil and gas from younger rock layers to start working their way up through fault zones. Hopefully we don't lose it all at the surface. We can drill down, excavate it, and get it out without much minimal effort. When we think about the Tejas Transgression, I think it's noteworthy here to point out that this is such a prolific amount of salt. We've used the salt, and second of all, we've used areas that we've mined out the salt to store a whole bunch of the oil that we've gotten from this as an emergency backup plan for the United States, to be exact, around 457 million barrel capacity. So if you weren't aware of this, that's located in parts of Texas and Louisiana, and this reserve comes from these aged rocks. And the oil and gas is from the Cenozoic rocks, but the ability to get it out of the ground came from the Jurassic Luan salt domes. Fascinating stuff. So as we conclude the topics of the Paleogene and Neogene plate tectonics, a couple of key things happen. Remember, we had two orogenic belts that were global that would create major orogenies in Asia and Europe. The Alpine Himalayan orogeny, which lifted the Himalaya range, and then of course the Circum-Pacific orogeny, which is famous for the Ring of Fire. The Columbia River Plateau area is famous for all the flood basalts that happened, and then we know the Laramide orogeny uplifted the modern-day Rocky Mountain Range and also impacted the northern Canadian Rockies. We know the Basin and Range province was created. We know, by the way, from tension, stretching of the crust. Same thing with the Rio Grande. A little bit later it formed and it created a very important rift zone still active today. We also know that there was volcanism in the interior of the continent where Devil's Tower, this feature right here, was made in eastern Wyoming. San Andreas Fault was born because of a complex set of subduction zones that relocated, making a transform plate boundary along Southern California. The Appalachian Range experienced some uplift, but that was mainly caused by differential weathering. And then, very important story is the Tejas advancing 8 and retreating 8 consecutive times. That 8 number is like a test question, very important to understand that there were minor transgressive and regressive cycles. When I come back to visit with you about the Quaternary, it's a fun time because we'll be learning about the Ice Age. So I hope to see you back for the next lecture series, and take a break. See you back then. Bye.